Let's get started. So the last class we were looking at this idea of multiple input, multiple output, nonlinear PID control, where the objective was that I don't want to just look at controlling one mode of motion individually, but I wanted to see how I can control multiple modes of motion at once. So if I wanted to design a controller which would control multiple modes at once, how do I go about designing it? We were looking at the generic equations of motion of our craft. So this were our kinematic equations, and these represented our dynamic equations of motion. And we are assuming here that the states are completely known to us, which means that eta and v, which means the positions and velocities, are either measured or we know precisely what their values are. So one of the two is either happening. Either we are directly measuring them or we are estimating them from other measurements from our sensors. We defined this nonlinear controller tau as our control output. So this is the thrust that we are providing. Okay, so thrust that our controller provides is given as g of eta, so where we are kind of compensating for these gravity terms, if at all there are any, which I told you was more relevant when we are looking at underwater vehicles and less relevant when we are looking at surface crafts. So because we know that there is no stiffness term in the surface crafts, especially in the surge, sway and yaw modes, this term will not be present when we are looking at a 3 degree of freedom model for our surface craft. But it will be important when we are looking at underwater vehicles, or if we were looking at 6 degree of freedom control, we would see those effects come into picture. The second term now is what our PID controller is doing. So we are having a difference here being that I'm having this pre-multiplication with j of theta transpose. So I'm considering the kinematic equations and looking at this J matrix, and I'm pre-multiplying my thrust vector determined by my PID control law by this J matrix. And you'll see that the idea of doing this is so that it will help us prove Lyapunov stability for the system, which is why we are going ahead with this nonlinear control law. Notice that it is nonlinear on account of the fact that J contains trigonometric functions which are not linear in nature. So we specify our PID again in our usual form, whereas now instead of the scalar form, we have the vector form where Kp, Kd and Ki are gain matrices. So rather than being simple gain values, scalar gain values, these are gain matrices. You'll typically choose these to be diagonal matrices. For most practical applications, you'll choose them to be diagonal matrices. We'll not ever, most likely you will not see applications where we will choose a full matrix of Kp, Kd and Ki. Most likely they will be diagonal matrices. And you'll see that this Kp is multiplied by the error in eta, Kd is multiplied the velocity, eta dot, and then Ki is multiplied by integral of the error over time. Again, as before, we were looking at the idea that when Ki is 0, let us see what is happening to the system. And we can see that the closed loop system dynamics in this case is governed by m times v dot plus c times c plus d plus kd star times v plus j transpose times kp times eta tilde is equal to 0. Notice that what we have basically done is taken this PID law, substituted it here, and whatever is the resulting expression, we have substituted it into our differential equation. And we are looking at what is the total system, what is it looking like. So you have seen this term there, C plus D plus there is an additional term which is coming as J transpose times KD times J. And that is becoming your KD transpose term. That's what is coming into the picture, into your damping now when we are considering it. And then you have your J transpose Kp times eta tilde. All of that multiplied must be equal to 0. That's what we get. The idea was to show that this system is Lyapunov stable. So we assume that for now we are looking at a regulation problem such that the desired trajectories derivatives are equal to 0. So eta d is equal to constant, and we are trying to regulate our eta to tend to this constant value of eta d. So you can think of this as a so-called station keeping task, where I have given a specific location of a position and an orientation which the vehicle needs to maintain. And I just need to make sure that my position is there and I'm maintaining that orientation. So the Lyapunov function in this case could be constructed as we have seen here, 1/2 times V transpose times M times V, and 1/2 times eta tilde times Kp times eta tilde. And I told you that there is a transpose here which is missing. Okay, so eventually giving us the fact that V is now a scalar function. This capital V Lyapunov function is a scalar function. We are assuming here that Kp is a constant matrix, which means it's not varying with time. And you'll see that that's not precisely true in the strictest of the sense, but we are able to get away with it with more or less. And you'll see that happen in just a minute. So Kp is a constant matrix which is positive, definite, and is a symmetric matrix. We are assuming that it's a symmetric matrix. As I said, typically we choose these to be diagonal matrices, so therefore they will be automatically be symmetric as well. So by taking derivative of this Lyapunov function, we observe that we get this form V transpose times something, and this something is actually seen that these two terms are there in our closed loop system dynamics. They are basically the first term and the last term. So I can express the combination of those two as the negative of this term, and that's what we're going to put it back in there. So you're going to see that it becomes minus V transpose times some matrix times V. And since our damping is going to be more or less positive in the system, we can assume that this product minus of V transpose times D plus KD star times V must be less than equal to 0. Notice here that the Coriolis term does not contribute anything because the Coriolis matrix is skew-symmetric, and we have shown that the quadratic product for that will be precisely equal to 0. Okay, and therefore we see that the system is at least locally stable, and we first try to observe when is this V dot equal to 0. And we see that the set of points where this V dot is equal to 0 corresponds to where eta tilde and V are chosen such that the value of V is equal to 0 will give me the fact that this V dot is equal to 0. So that is the total set of points where V dot will be equal to 0. We see the idea that whenever V is equal to 0, we'll see that M times V dot is minus of J transpose K times eta tilde, which is coming from our closed loop system dynamics. So whenever V is 0, this is the equation which still has to be satisfied, indicating that V dot will be non-zero as long as eta tilde is non-zero. So whenever eta tilde is not equal to 0, V dot will be non-zero. So this means the fact that whenever I start at any point where eta tilde is non-zero but V is equal to 0, that point cannot be an equilibrium point because the system cannot be stuck at that point. Because at that point V dot is non-zero, at the next time instant I'm going to observe that V dot will be changing its value. So therefore the only equilibrium point in this invariant set, the largest invariant set of this omega, is the equilibrium point eta tilde and V both being equal to 0. And therefore by our Krasovsky's-Lascelles theorem, we know now that this point has to be globally asymptotically stable. So which tells us the fact that the control law, the PD control law which is chosen ensures that the 0, 0 error point is tracked really well. Again, when we start adding integral action is included, we can show that the system is at least locally asymptotically stable, even if it is not globally asymptotically stable, because the integrator does add a few dynamics into the system which can render it unstable if the gains are not tuned properly. Okay, so with that keeping in mind, we get the idea that the integral action is needed to compensate the disturbance effects to 0, so the steady state error to be driven to 0. But what we lose is the fact that we are not able to guarantee global asymptotic convergence. We are only able to get a local asymptotic convergence. But one has to make this compromise between the two of them when we are designing the control system in order to see which one gives us the best fit for our problem. Okay, so let's kind of try to formalize this multiple input, multiple output pole placement algorithm. And you'll see that in this case, our systems dynamics, closed loop system dynamics was given by this, we had seen before. Now we'll assume here that J dot, okay, which is the fact which is coming from our kinematics equation, which relates eta dot is equal to this times v. Okay, I'm basically taking a second derivative of this. So let me try to show that. Okay. So I have my original system, which is m times v dot plus c of v plus d of v plus kd star of v times v plus j theta transpose. We put this transpose here times kp times eta tilde is equal to 0. This is my closed loop system dynamics. Now what I want to do here is I want to introduce, or I want to use my idea that eta dot is equal to j of theta times v, and I want to differentiate this. So if I differentiate this with respect to time, I'll get eta double dot, and that will be equal to j dot theta times v plus j of theta times v dot. Everybody with me so far? Now we assume that the Euler angles are not changing drastically, so at least we'll assume that this derivative term is approximately close to equal to 0. Okay, we are assuming that our angles are not changing too drastically over time, which means we are looking at mild trajectories which are milder in nature. In which case, I can say that eta double dot is j of eta times v dot. Okay, or which means v dot is given by j theta transpose of eta. Sorry. Yeah. Inverse times eta double dot. Now, once I know this v dot in terms of eta double dot, I want to plug that v dot into my closed loop system dynamics. Okay, why do I want to do all of this exercise? Because I want to get it in the form of a spring mass damper system. I want to be able to compare it with a spring mass damper system and then specify this pole placement method which we have been looking in the scalar case. I'm basically extending that to the vector case in this scenario. So using the kinematics of the system, I can put v dot into here. What do I get? I'll simply get m times j of theta inverse times eta double dot plus I have an additional term which is coming into the picture here. So what I'll basically do is I'll also pre-multiply this entire equation by something else. Take J transpose of eta inverse. And you'll just see in a minute as to why am I doing that. So I'm pre-multiplying the whole equation by this term. Okay. So then what will happen here? I'll have that extra terms come into picture here, right? J theta transpose inverse times C of V plus D of V plus KD star of V times V. Okay, now that V can be replaced by J theta inverse times eta. Everybody with me so far?
Is it's eta dot, right? I think.
Sorry, come again?
Should be J inverse eta dot, right? Because we are.
No, this one is this. Which one? Here?
We substituted V with J inverse.
Correct. So this will be
eta.
It has to be J inverse times eta dot. And then finally, then we'll be left with the fact, this last term, because we are multiplying by the inverse of this thing will go away. What I'll be left with Kp times eta tilde. Kp times eta tilde is equal to 0. Okay. Now I want to compare this system with a typical spring mass damper system. So let me see where I am. So when I multiply by that entire thing, this is what we got. J inverse M times J transpose inverse times M times J inverse times eta double dot plus J transpose inverse times C plus D times J inverse times eta dot, and I've actually separated out the KD term separately, because remember when we had looking at KD star was nothing but this fellow, right? So when I'm actually trying to understand what is happening, I'll get J theta transpose inverse pre-multiplied by this fellow. So those two will cancel out. And what will be left with KD times J of theta. KD times J theta times J theta inverse times eta dot. Is that making sense? Tell me if it's not making sense. I'm basically trying to compute pre-multiplying by J of theta transpose of eta inverse of KD star times V. This is what I'm evaluating. This thing will become this. That's my contention. Okay, so where we have used the kinematics at the last step here to transform V into this fellow, and then we have used the KD's definition, KD star's definition here, and we have pre-multiplied it by J transpose inverse. So eventually, after the cancelling out of the matrices, this is what we should be left with. Okay, so at the end of the day, what I'll be left with is this term which you saw before plus KD times eta dot, and then I'll have KP times eta tilde. Okay, so this becomes my equations of motion expressed completely in terms of eta. Now what we will do is we'll basically compare it with a spring mass damper system. Okay, so we are basically comparing it with a vectorized spring mass damper system as if it's having multiple degrees of freedom. Okay, so we have some mass matrix times eta double dot plus 2 times some damping ratio times natural frequency times the mass matrix times eta dot plus omega n square times mass matrix times eta tilde is equal to 0. Everybody with me so far? Where we are trying to compare between these two. So now we will take term by term comparison, and you will basically see that this M star, the so-called mass matrix, is nothing but J transpose inverse times mass times J inverse. J transpose inverse times mass times J inverse. That is what gets multiplied with eta double dot, right? So that becomes my new mass matrix, or the so-called notional mass matrix. And then this leads to the idea that 2 times Z times omega n times M star, okay, 2 times M star Z times omega n is nothing but that so-called damping term which we had in our system. We are equating those two damping terms. And finally, whatever is the stiffness term, which is M times omega n square, is the stiffness term, which in this case turns out to be simply Kp matrix. Everybody with me so far? Yes, no? No? Come on guys, respond at least yes or no. If it is a no, then we can go back.
It is clear, sir.
It's clear? Anand, clear?
Can you go to the last equation? Previous one.
This one?
Yes, so we are comparing this with the spring mass. That equation.
Correct, correct. So this basically becomes my mass, right? So that becomes M star. And this becomes my so-called damping term. So this is 2 times M star times the damping ratio times omega n, right?
Yes.
This plus this one, okay. KD term also will be figuring into this, right? Because that is also a damping term, right?
Hmm.
And then finally the Kp term is nothing but M star times omega n square. Right? So that is what we are making the comparison. So eventually we should see that our M star is our so-called notional mass matrix. 2 times M times Z times omega n becomes this damping term which we saw before plus Kd, and then this fellow simply becomes the stiffness term.
Yes.
Okay. Okay.
Yes.
Which can now be used basically to solve for the gains Kp and Kd. So let's try to formalize what is that which we are doing. We have looked at a lot of equations, but let's kind of formalize the steps. Typically what will happen is we want to place the poles of the system at a particular location that will determine what is our damping matrix and the natural frequency matrix. That will determine where should my natural frequencies of the different modes be and where the damping ratios of the different modes be. Correct? Once I know those values, I can compute the gain values using these inverted expressions from here. So I can solve these two expressions to find out what is my Kp and Kd. Once I put those values of Kp and Kd into my control law, it will ensure that my system has a PID control law which is trying to track my system to be similar to a spring mass damper system. that making sense? Bear with me just for one more minute. It will become clear. Okay. So if I wanted to specify what we would do, we would either need to specify the natural frequencies, but typically in a control system, we would specify in terms of the bandwidth, right? We know that the bandwidth and the natural frequencies are related. So if we are specifying a matrix of the bandwidth for each of the 6 degrees of freedom, and we are specifying a set of damping ratios, zeta 1 to zeta 6, then we can compute the natural frequencies for each of the 6 modes. Yes, once we know all the natural frequencies and the damping ratios, I can then compute the KP matrix because I know everything here, right? Are you following me? Is everybody following me?
Yes, sir.
Aditya?
Yes, sir.
Yes? Okay. All right. Then I can similarly find out what is the KD matrix by just inverting those relationships which we had, right? Whatever we had before, these expressions, I'm just solving for Kp and Kd. Kp is simply m times omega n square. Kd will be this term minus this term, right? That's what we should see here. This term minus this term. Okay. So once I know the Kp and Kd values, I can compute the integral gain by using our thumb rule that it should be at least 10 times lower than the proportional term, and then I have found my gain matrices Kp, Kd and Kl. Okay, and then basically with this system I should be able to ensure that the steady state error goes to 0, and therefore the system tracks whatever the waypoint which I have given it. So if I gave it a station keeping waypoint, it ensures that it should go there and stay there. Notice that here we have assumed that eta d is more or less constant. But the same can be shown to be equally valid when we are having eta d being slowly varying with time. Okay, unless until it's quickly varying with time. So that's fine. But one thing to note here is that in our Lyapunov system, we originally assumed that Kp matrix is constant and symmetric. Right? We used that idea in the proving of the control law that it is stable. But then if you really look at our Kp matrix now, it is m star of eta times omega n square. Okay, omega n square is fixed because I know where the natural frequencies of the systems are located. But m star is not fixed. Okay, because m star is what? M star is basically that j theta transpose inverse times the mass matrix times j theta inverse. This is what is that m star matrix. So even though m itself is not varying with time, j of theta may be varying with time. So therefore m star may vary with time. Okay, so that we have landed up ourselves in our trouble now, saying that, hey, if Kp is not fixed, how do you make sure that your control law is still valid? So here is where we will make that assumption that if j dot of theta is relatively small, then I can assume that Kp dot will be relatively small. And why am I able to do that? Basically, if you go back here, we are using that idea that j dot is relatively small in our Lyapunov stability anyway. Okay, j dot is relatively small. And then now we are saying that if j dot is relatively small, then our Kp matrix, which is nothing but m star times omega n squared, correct? The only variation is coming from the M star. The time varying component is coming from M star. And we just saw M star is basically this J inverse times M times J inverse. So as long as J is slowly varying, I can argue that these two matrices, which you see here, one here and one here, they are also relatively slowly varying. They're not changing that quickly with time. Right? So if they are relatively slowly varying, M star is relatively slowly varying. So therefore M star times omega n square will also be relatively slowly varying. So under the assumption that my Euler angles are not changing very quickly, I can say that my Kp is not varying very quickly. Okay? Or Kp dot is kind of close to 0. Which means that over a relative portion of time, you'll see that Kp is fairly constant, so our analysis still holds. Okay, it only holds as long as this J of theta, J dot of theta is not quickly varying, which means the Euler angles are not changing very drastically over time. So we are not looking at aircraft dynamics where we are looking at G forces come up because the spin rates are so high. All such sort of things are unlikely to happen with respect to ships, so we can get away with that fact. But if you wanted to apply the same dynamics to the aircraft dynamics, like a fighter jet's dynamics, then you can't apply them as successfully. So let's say that you are looking at some 8G maneuvers or 4G maneuvers, then you can't apply these things. You have ever seen the idea that there is this G test which is performed? I don't know how many of you are aware about it. For aircraft pilots, they perform this G test. You're aware about it? Yes, no? What is that G test?
Basically, like there's a device in which the person sits and like the device like rotates very fast or something.
Yeah, it's basically a centrifuge.
Centrifuge, yeah.
They put them in a centrifuge and then they make sure that the centrifuge is rotating at heavy speeds, so resulting in very strong accelerations acting on you, and your body must try to survive those accelerations in order to make sure that you don't pass out, right? And I think the largest one has succeeded in doing so far is about 9 Gs. 9 Gs is like the limit of human body. Beyond that, the man will pass out. Basically, he will just go unconscious. The forces are so strong, and it's very interesting to see that when you are having these extreme G environments, you barely can lift your hands, limbs, and anything, because you just imagine your hand weighs now 10 times its weight, right? So then it becomes so much more difficult to react to situation, and that's a big concern, because if they have to make any reactive maneuvers at those speeds, it's really hard for them to move their limbs and be able to get away from it. But in all honesty, for ships, we'll never experience such sort of extreme G forces. So we are safe to say that our J dot may be close to 0. So which means that our analysis is more or less valid for fairly a good amount of deal of things.
Sir?
Yes.
Then how is this nonlinear PID applied in those aircraft dynamics?
Oh yeah, so if you want to apply for the aircraft dynamics, you have to include the fact that J is non-varying. J is varying with time.
Yeah.
And then you have to design your controller law accordingly.
But the Kp in that case will be also...
Correct. So Kp will be time varying in that case. You'll have to think of a better, cleverer approach. So you have to look at aerodynamics papers if you want to really figure out what they are doing. But it's quite a challenging problem. It's not as easy as it looks. And also the other aspect is that most of the ships which we look at are straight line stable, which means that without any open loop control, the system is stable. Right? In the sense that what I mean is, if I want to give certain amount of rudder, I usually get to see a certain amount of turn rate. But that may not be true for aircrafts. Without a feedback control, they may be very unstable. It may not be flyable without a control system in place. They are designed such that so that they can be highly maneuverable. So if you're trying to fight out with another, so if a MiG is trying to fight with an F-22, you don't expect that if I want to make a turn, it will take 5-10 seconds to slowly turn. He'll have nice little time to target us, fix up a lock, and then hit us, right? So you don't want to do that. You want to be highly maneuverable. So there the system is much more complex. So there what they will do is probably, my suspicion is that they'll have multiple loop closures that we discussed. They'll not be just limited to 2 loop closures, but they'll have multiple rounds of closures in between in order to make sure that they can stabilize the system in some way. But it is quite an interesting problem. In fact, even if you're just looking at a quad rotor dynamics, that itself is not quite straightforward to look at. It's quite complex in itself because it's an underactuated system, highly underactuated system. You have 6 degrees of freedom to control and you have only 4 rotors, right? So therefore, it can be quite challenging to look at. And there you have to come up with more complex control laws. And as I said, usually it will be done either using loop closures. That is the typical way most industrial applications will look at. Or if you are a mathematics professor, some might come up with extreme mathematical control laws, which may look extremely good on paper, but then their practical applicability can be a little under the wind. Okay. Sometimes a balance between the two is also sometimes seen. There you might be even looking at one question which I can answer you in that case might be Aditya, is you may look at sliding mode control or things like that. Okay, where you're kind of saying that whatever be the dynamics of the system, I don't care, I'm going to force it to follow certain system dynamics which I want. And then I'm applying a whole load of control, control computation, which I need to get in order to make sure that my system follows the dynamics which I intended to follow. Again, there you have to prove stability again from this Lyapunov perspective, but then it's no longer PID control. So to answer your question aptly, it would be that your PID probably will not be used there. You will be requiring really stronger, much non-linear control laws in order to make those maneuvers happen. They definitely are not using typical PID controllers. Okay, you can't achieve that. Good thought process though, good question. Okay, so the idea here then becomes that once we have these, assuming that this j of theta is slowly varying, our kp dot is approximately equal to 0, and the proof holds reasonably under this assumption. But again, it has to be taken with a pinch of salt because as we saw, the moment we introduce any integral action, we are losing our global stability properties pretty quickly, and we are limited to a local stability properties. But as long as the region of convergence is fairly large enough, we may not be so much worried, unless until the region of convergence is very small and the local stability might be good enough. I'm not quite sure. Many of you have watched this movie called Top Gun. Have you seen the movie Top Gun?
Yes, sir.
Yes, sir.
Yes. Some of you have not. It's worth a watch. And there you will see some amazing stuff about maneuvers. And actually, I believe there's a sequel coming. Am I wrong?
Yes, sir.
I think it already is.
Yeah, Top Gun Maverick is coming up, right? So it's quite interesting to see. If you look at the trailers, especially for the newer movie, you can see the G forces acting on their faces. You can see that their faces become soggy and all when they are executing G maneuvers. So it's quite exciting to see that. All right. Okay, so now that we have covered the so-called control systems and the linear and non-linear PID control, we'll try to take a look at a few case examples. Okay. Today I'm only going to cover some basics of the basic elements of this heading autopilot. In the next class, we'll take a look at what are the mathematics behind it. We'll kind of see how our guidance, control, and everything is coming into the picture. Okay. There is a missing component here though, which is the navigation, which we didn't talk about. So we will be spending some amount of time to discuss about navigation in the coming lectures. Okay, so a typical heading autopilot for a marine craft will have some of these 5 or 6 different components that we are going to talk about. So the first system is the control system, and this provides the necessary commands to track the desired yaw angle. So that given a desired yaw angle that I want to achieve, so desired heading angle that I want to achieve, your output is basically what is the yaw moment I need to apply to the system. Okay, you can think of it as a cascaded part of a controller where I'm seeing at what is the force that I need to apply, force or moment that I need to apply onto the vehicle in order to make sure that my desired heading angle is achieved. The next aspect becomes the control allocation problem, which means that given a particular yaw moment, which I want to find out, how can that be achieved using the different actuators on board the vessel? And there can be different actuators. For a typical single screw ship, the only actuator will be the rudder, which will affect your yaw moment, right? Propeller will not generate any yaw moment on a single screw ship. But if you had, let us say, a bow thruster in conjugation with a rudder, then you could say that, okay, if I want to achieve so much yaw moment in a hull, I can kind of separate that into how much rudder should I apply and how much bow thruster should I apply. Okay, so that becomes the control allocation problem. Now my PID law is telling me what should be the moments that I need to apply, but how do I get that moments from my actuators? That is what is the control allocation problem. So we are distributing the feedback control system's output, which is our, in this case, will be the yaw moment that I need, to the actuators like the rudders, thrusters, and the propellers on board the vehicle. The third aspect, the third component of our autopilot system will be this reference model. Now we are talking about the guidance system. This is what will tell me how to compute the desired heading angle, the desired yaw rate, and the desired acceleration. Okay, in case if I'm looking at smooth course changing maneuvers. The course keeping maneuver is a special case of this, which means I want to keep the heading angle as a constant is a special case of this, where psi d is simply constant and rd and r dot d are both 0. Okay. So our guidance system will really come into the picture here. So just to look back, we had the control system, control allocation system, and the guidance system. Now the next part is the yaw rate and the compass sensors. Typically, you want to measure what your heading angle is. You have to get a feedback from somewhere. So you need sensors which will provide you the feedback. With respect to yaw, that can either come from a compass, that is what was traditionally used. So since years, thousands of years ago, magnetic compasses have been around. But in the newer ships, now we have gyroscopes. Okay. So the gyroscopes do not give us the yaw angle directly, they give us the yaw rate. Okay, so they give us the yaw rate which can be integrated in order to get the yaw angle. And many a times we are looking at a fusion between the IMU, where it is looking at the accelerations and the angular velocities being fused together in order to obtain a orientation vector or the quaternion vector. Again, that is not valid when you are discussing about your aircrafts. Okay, that is where it will fail. Because all of this is assuming that the gravity vector is pointing always straight down. But if my craft is maneuvering at 4G or 5G, then accelerations itself are more than the acceleration due to gravity. So in that case, the orientation vector cannot be obtained using the methods which are used. So which means the sensors that we generally have on our marine craft, they are not suitable if you want to apply or scale them up directly to the aircraft dynamics or high-speed aircraft dynamics. They will require some other algorithms in order to do the fusion. Okay. That's why that field is so rich, and you have seen a lot of development with respect to control can be attributed to the aircraft dynamics. Okay, so compass and yaw rate are our typical sensors, what they will measure. But then we need to do a state estimation. What do I mean by the state estimation? Here we are measuring the raw measurements of the compass or the raw measurements of the yaw rate will not only include the slowly varying yaw, but they'll also include the so-called wind-based disturbances or wave-based disturbances as well. So let's say that our vessel is operating in waves, then the waves itself will cause it to have some oscillatory yaw motion, which will be superimposed on top of our slowly varying yaw motions, right? And when we are trying to define our controller and we want to give a feedback of our current heading angle as a feedback to our control system, we do not want to give this oscillatory behavior of first order wave systems. We do not want to pass them back to our controller. We don't want to pass them back because if our yaw rate is very quickly varying, then our rudder will be trying to compensate for these dynamics by quickly varying itself. And that will cause a lot of wear and tear on our actuators, which we don't want to. I mean, it's only an oscillatory behavior which we are not really interested in. We want the overall heading to be more or less constant. So we have to kind of filter out these low frequency stuff from the measurements and eliminate them and only pass what is left out as our feedback system to our controls. Is everybody following me now? We don't want these first order wave dynamics to be passed back into control system. Okay, so that is where we will require what are called state estimators, and we did not talk about them as yet, but we are going to speak about them in a couple of lectures time. Okay, the idea there being that we are able to estimate what is the low frequency component of the signal, and you can either be doing this by simply passing it through a low frequency filter, or you can use something like a Kalman filter where you're trying to get the best estimate of your current low frequency heading angle. Okay, once those two are estimated, so once I have the sensor measurements which are passed through a state estimator, I know what those values are, I can feed them back to my control system in order to take care of the control. Sometimes it is also important or interesting to include what is called as the wind feed forward system. So what I mean by that is I have a wind sensor is available on board the vessel where I'm measuring the wind speed and the wind direction, and I'm trying to figure out what my control law should be. I'm having this extra term in my control law to compensate for the wind forces. Now one might wonder, why do I need this? Isn't there an integral action already there in my controller which will compensate for this? We know that it will compensate for any of these steady state disturbances. That is why we had the integral action to begin with. The point is, integral action will only start when there is sufficient deviation from your course, right? Because it is based on feedback mechanism, only when your heading angle has changed considerably that your feedback mechanism will try to push you back. But what we are trying to do here is, based on the wind speed and the direction, if we can compute what is the amount of force which is going to come onto the vessel, I'm trying to compensate for it immediately. So I'm not trying to see a big overshoot in the error by trying to take an anticipatory effort. Okay, so I'm based on the wind speed and the direction, I'm anticipating that this much force will come and I'm counteracting it right away so that I don't deviate much from my course. So it's much faster. Whereas if I were to rely purely on the feedback mechanism, I have to deviate from the course, only then my feedback will kick in, trying to push me back into the same heading. So it is normally very common to see these sort of wind feed forward systems put into place so that you can compensate for these dynamics ahead of time. If you remember the accident which happened with the Ever Given ship in the Suez Canal last year, right? There was a huge sandstorm which caused winds upwards of 50 meters per second, which now caused the ship to suddenly veer off course and then get wedged in the Suez Canal channel. So if you have a very strong wind feed forward system, I'm pretty sure they had it too, but it just exceeded the limits. So you're not able to compensate for the thrust in due to the wind ahead of time, and it started veering off course. So if you have a strong wind feed forward system in place, you can try to anticipate these loads which are coming onto your vessel and compensate for them. That is the main advantage. But then the challenge is you need a model for the wind. You need to precisely be able to compute based on a wind speed and a direction, how much wind force am I going to experience. You have to have some estimate of that. And that computation has to be done online, which means there is a computational overhead that you're adding by including this feed forward mechanism, which was not there when you're only looking at a feedback mechanism. So again, it goes that it's a compromise. I gain some and I lose some. What do I want to gain and what do I want to lose? And you have to make a perfect compromise between these characteristics depending on what is your requirement as a control engineer. All right, with that in place, we will kind of stop here, and in the next class, we'll try to look at the how the mathematics of everything is tying up together in a brief sense. We'll try to look at one with respect to a heading controller, heading autopilot, which are using low frequency filters. And we'll also look at one example, which is using LOS guidance scheme to determine our heading angles. Finally, we'll also discuss one more model for our dynamic positioning systems, which is what this course is primarily about. So we'll have a small discussion about that before we head off into the navigation systems. Okay? So you can expect maybe one or two more lectures to finish off or wrap up the control systems for now, and we will be then moving on to the navigation systems. At least one good thing has happened in today's discussion is Aditya's question has given you the perspective that PID cannot solve all problems, especially when you have very complex systems, which is where you require more nonlinear control laws to be executed in place. Okay? And that is where we will see those nonlinear control mechanisms come into the picture, which we are not covering in this course because we want to focus a little bit on navigation systems, but you can definitely read about it and see how these can be implemented on the vehicles. Okay, any other queries before I stop recording? If not, I'm going to stop recording.